from origami to design, foldable structures, and we have compliant mechanisms as well, right? Which are mechanisms that have flexible members and do not need any assembly, right? So we'll take an in-depth look within the area of biological and rehabilitation robotics first. So what is this area about? It's a natural question that would come to our mind. So this is a field basically which combines knowledge from three other fields: biomedical engineering, cybernetics, and robotics. So the main goal here is to develop efficient systems that leverage the millions of years of natural evolution that has happened within nature. And in order to develop such efficient systems, we use uh, the information from biological systems in order to aid the society and ultimately help the development of the field of medicine and healthcare. So there are some challenges within this field that one must tackle. One one may tackle, right? So if you wish to get into biological and rehabilitation robotics, you may try to mimic biological tissue that has sensory capabilities. So let us take an example of our skin. It is one of the most sensitive organs on our body. It can sense pressure, contact temperature. It can sense the roughness of a surface as well, and it can characterize surfaces based on the particular texture that we have. So mimicking this capability within a synthetic material with sensors is quite challenging, right? And then we have uh, a challenge within the area of brain-computer interfacing. So developing a robust, real-time, and a non-invasive brain-computer interfacing system has been a challenge for quite some time. Here, non-invasive means that one need not install a particular chip on inside one's brain for the brain-computer interface to be active, right? So then, thirdly, we have development of artificial muscles. So within this area, there have been a bit of success with materials like shape memory alloys, and those materials have quite a bit of load carrying capacity as well. But their operation, the speed of operation is quite slow, right? Because their operation, especially when it comes to shape memory alloys, it depends on the ambient temperature and the corresponding change in crystal structure and so on. So developing fast artificial muscles and that have a huge load carrying capacity as well has been a challenge for quite some time. Then developing safe programmable nanorobots is also a problem because nanorobots have potential at targeted drug delivery within fields like cancer treatment. So currently, there are very few frameworks for safe and programmable nanorobots. And why do I emphasize upon the word safe? Because these nanorobots are basically very tiny robots that have capabilities in interaction with the immune system of a person. So if they cause a negative reaction with a particular person, then that would be safe for the person's health, right? So developing safe and programmable nanorobots is a challenge. Then in every area, I'd introduce you to some resources, video resources that you can watch. And here on the left hand side, you can see xenobots. So these are robots basically which have been constructed by an assembly of living cells, living biological cells. So how exactly these xenobots were made? Uh, you can watch this video that I've linked here, and below it you can see a prosthetic arm that was developed at the University of Michigan, and which has mind control capability as well. So I'd recommend you to watch these two videos later on when the slides would be shared. Okay. So what skills do you need within this field? Firstly, you need a creative mind and good observational skills because you you would ultimately be modeling biological systems. You would be observing them. You would be characterizing them, right? So you need good observational skills for that. And secondly, you need a bit of ROS experience, C++ or Python. And there are a few specialized frameworks like the soft robotics toolkit in this case, which would be useful. Okay, so Now you need an understanding of finite element methods as well in order to do this corresponding simulations and stuff. Slight knowledge of biomechanics and ergonomics would be a plus, and you also need to have a working intuition on materials, their pros and cons, and how they are used within the industry and how they serve the purpose in a particular robot. Okay, so coming to the avenues for jobs, you could work at these companies if you wish to get into biological and rehabilitation robotics. There's Procept Biorobotics, Accurate, Intuitive. So this is the company which developed the Da Vinci surgical robot, right? So we have Centroid Motion Capture, which obviously does motion capture, but has worked with the Hollywood industry and involves quite a bit of common knowledge to biological and rehabilitation robotics, especially biomechanics. Then we have Revok, which develops prosthetics, leg prosthetics, and Med Robotics, which also develops surgical equipment. And for the avenues for higher studies and research, you could go to, there are various groups throughout the world, and you could go to Imperial College London. You could go to CMU, EPFL, which is in Switzerland, the University of Vermont. There's a neuro robotics lab there, and this is the place where the xenobots were actually made. So then we have Georgia Tech, FU Berlin, and within India we have the soft robotics lab at IIT Delhi, and you can even go to IIST Shibpur as well. So this is the info for biological and rehabilitation robotics. So now let us take a look at autonomous systems. What are these systems, right? So basically, these are agents or robots, basically, which accomplish a desired task in a potentially unstructured environment, and they do so without any human intervention. And so, where would you actually use these systems, right? That's a question to ask. So, we can use these for rescue or delivery operations. Self-driving cars, of course. On the left, you can see the autonomous car built by Waymo, which is a company in the US. You can see it in action here. It's detecting all the uh, you know cars around it and based on the camera feed as well, and it's path planning as well. Correct. Then we have underwater mine diffusal and exploration. You can use autonomous systems for that purpose as well. Now, there are a few significant challenges within this field that you may tackle, right? So, first problem is robust localization under GPS denied environments. So let's just say you were traveling through a tunnel and you were sitting inside an autonomous car, which is relying on the GPS for localization and no other system. So naturally, inside a tunnel, there won't be any GPS signals, right? So you would lose your ability to localize and ultimately control your vehicle, and this would lead to accidents naturally. So this is a problem that we have to tackle. And secondly, we have perception failure under distributional shifts. So this means that let's just say we have a vision stack that was developed uh, in US, for example, and the data for training the vision stack was obtained on the roads of California. If we deploy that same vision stack on the roads of India, then do you think would it work? Naturally, it won't because it's training data. The data that was used for training the vision stack is naturally different from what the stack would observe on Indian roads. Naturally, there would be uh, different kinds of trees, different kinds of animals on the road, and the behavior of pedestrians would differ as well. Correct. So that is a challenge. Then ensuring universal safety on roads. Basically, your autonomous system should not discriminate between any particular obstacle. Let's just say we have cars, trucks. Your vision stack is perfect in detecting those, but it misses cyclists from time to time. Then this would lead to hazard for life on the road, right? So that's a challenge. And finally, we also have to develop a legal and ethical framework for autonomous systems in the decades to come. Because if you get into an accident and you are sitting inside an autonomous car, who is to blame? Correct. So that's the problem here. And I'd recommend you to watch this video, which is a talk that was delivered on Tesla AI Day, and it explains the architecture and working of Tesla's perception stack that is currently being used within Tesla models. So that's an interesting talk. I recommend you to check it. And the skills you need to work on autonomous systems. So you need ROS 1 or 2 experience, C++ or Python, and you also need experience with simulators like Ignition Gazebo, Carla, LGSVL, and of course you need experience with Linux. Then there are frameworks like OpenCV, which is for vision, CUDA for hardware acceleration. Then TensorFlow, Keras, OpenGL helps a bit as well, and you also need proficiency in machine learning, signal or image processing. Then familiarity with network concepts is also a plus, right? So then we have avenues for jobs. These are quite well-known companies. There's Waymo, Tesla, Nvidia, Google, of course, Uber, and India. And in India, there's Ola as well, and Apple, Huawei. And for higher studies or research, you could go to Stanford ASL. There's the Autonomous Systems Lab there, Ford Center for Autonomous Vehicles, University of Michigan. You could go to ETH Zurich, UCSD, U Toronto, UC Berkeley. In the UK, you could go to Cranfield University, where you could do an MSc in Autonomous Vehicle Dynamics and Control, MSc. So you could go to NavLab at CMU as well. So coming to multi-agent coordination and control. This involves, as I said, robotics farms and handling of those. So why should we care about robotics farms in the first place? This is because they have an ability to solve very complex tasks with collective behavior that is generally generated by very simple rules and interactions. And they are capable of adapting to their environment as well. Just imagine colonies of ants, the hierarchy within those, and how the communication takes place between two different ants, pheromones, and stuff. It's quite fascinating. So the applications for this area of robotics can be, search operations, mining operations, agricultural, foraging, modular robots, which can reconfigure themselves based on the task at hand. Then there's the problem of microplastics removal from the ocean, right? So there are a few challenges within this field as well. Managing computational complexity with increasing swarm size. So as the number of robots in your swarm increases, the number of communications that you have to do, number of computations, path planning, everything goes as the order of n square, right? As the swarm size increases. So we need effective decentralization in this case. Thus, we need to determine an optimal communication topology for a given task. This means that we have to determine for a given task which robot should communicate with which other robots to accomplish the task with the minimum possible communication, and the task should be completed as well. So that's the problem for finding optimal communication topology. And thirdly, we have to prevent adversarial attacks on the swarm. Basically, we have to we have to build resilience against such attacks which disrupt the functioning of the swarm and thus jeopardize uh, the the task completion basically. So within the watch section, I would recommend you to watch this TEDx talk on swarm robotics by Magnus Egerstedt. It's almost 8 years old, but it's still quite insightful. And the skills you need for handling robotic swarms is, firstly, you need to have fascination with swarms within nature, right? Then you have to have ROS experience, C++ or Python, and simulators like VBots or TeamBots. Then frameworks like CUDA, TensorFlow, Keras, OpenGL, similar requirements, and here network concepts are required, like significantly. So for jobs within Swarm Robotics, you could go to ARS Electronica, Locus Robotics, Unbox Robotics, which is an Indian startup, by the way. Then there's APM Swarm Robotics, Avid Bots. And for higher studies or research, you could go to NTNU, which is in Norway. Or there's an autonomous robots lab there. A few of my colleagues work there. That's a good lab. Then we have the Swarm Lab at NJIT, New Jersey Institute of Technology. You could go to Northwestern. You could go to Grasp Lab at University of Pennsylvania, Arizona State. You can go to Texas A&M as well. So moving on, we have the area of computer vision and perception. So what are the goals of like why should you care about computer vision and perception? So to make a computer understand a scene is quite difficult, and the underlying context, the features within an image, that is quite a difficult problem as well. So the goal of computer vision is to do that and enable processes like decision making and control, and that's basically what happens within autonomous systems as well. So applications of computer vision are like many. There are many applications. You could use these in biometrics, pedestrian motion forecasting for autonomous systems, medical imaging, and we have disease diagnosis. Based on that, there's relighting of scenes, scene summarization, right? And coming to the challenges that you would tackle within this field. Firstly, you have to address latency within real time or time critical applications. Respect You have to respect the hardware limitations and the storage limitations as well while doing that. The video camera puts out videos at frame rates well and above 24 frames per second, right? It might be 24, 30, 60, and so on. So your vision stack should be able to work at that frequency. It should not be so slow that it reduces your frame rate and adds latency to your system and makes it less responsive. So that's the challenge. Then ensuring generalizability and robustness under phenomena like object deformation, occlusion. So what occlusion is basically when one object goes behind another object, your vision stack should be resilient to that. It should not misdetect something, right? Then there may be differing illumination, which makes objects look completely different, distracting backgrounds, transparency, and reflections. So handling these problems within vision stacks has been challenging. Then you need to safeguard your vision stack against black box attacks. There have been cases where one pixel from the input data from the input image was changed, and it completely changed the classification output, that are called adversarial one pixel attacks basically. So you have to prevent that, and I'd recommend you to watch this new CNN based technique. CNN is basically convolutional neural networks, and this technique is based on CNNs, and it's used for low light photography, and it has worked quite well in that area. So on the left, you can see GIFs for multi-person pose estimation and image segmentation. Then skills you need for computer vision. Basically, this field is moving at a very high rate, and it's developing day by day, right? So you need to keep up with the newest advancements in the field. Then ROS experience is optional in this case. You need to know C++ or Python, and similar frameworks like OpenCV, OpenCLNGL, CUDA, TensorFlow, and Keras. And here, additionally, you would need familiarity with cloud platforms as well, like GCP and AWS. GCP is basically Google Cloud Platform, and AWS is Amazon Web Services. So, avenues for jobs, you can see a lot of familiar companies here. There's Facebook or Meta now. There's Oculus, Netradyne, Intello Labs, which both of which are Indian startups. There's Playment, IBM, and Nvidia. Then avenues for higher studies and research, you could go to UCL, University of Nottingham. You could go to Germany at the Technical University of Munich. There's Brown University. There's a Caltech Vision Group. You could go to TU Delft uh, in the Netherlands, and there's a Vision and Control Research Program as well at NTO in Singapore. So this is about computer vision and perception, and now we come to the sub area of planning, mapping, estimation, and localization. So why do we need this at all, right? Well, that's a perfectly valid question to ask. So in order to make decisions and plan on future actions, a robot has to know its current state, right? Without localization and planning, a robot may not be able to uh, gauge whether it's colliding with something, or it may damage something, or it would not be an ideal operation, right? So without localization and planning, it would pose a safety threat for humans, property, or itself. It may just fall off a ledge or something if it cannot localize itself. So applications include parallel parking, subterranean exploration, which is quite important for cave exploration and stuff, where humans cannot go very easily. Then warehouse operations as well. Then there are a few challenges within this area. Firstly, we need to prevent the state drift due to sensor noise and inaccurate measurements. This is basically, let's just say you have a robot, and it has a GPS signal, or it has an inertial measurement unit, which is used for localization, and every sensor produces some kind of noise. uh, like every sensor has a signal to noise ratio. So that noise actually leads to the drift in the position of the robot, even if the robot is not moving. So we have to prevent state drift in that case. And secondly, we have to provide safety guarantees under dynamic environments, which are subject to factors like kinematical constraints, which mean like uh, we have a car, it cannot move laterally like this because it's constrained by its kinematics. Then we have non-linearities, just like internal combustion engines are quite a non-linear system, and to give the right amount of throttle and stuff, that is quite challenging. And there's obstacle motion uncertainty as well. So under these conditions, you have to provide safety guarantees for operation. And I'd recommend you to watch this talk on trajectory forecasting. It's a recent talk, like in 2021 only, and it's presented by Dr. Boris Ivanovich, and it's quite an interesting talk. So on the left, you can see here's a SLAM setup in ROS, which uses rapidly randomly exploring trees for localization, and it's performing SLAM as well. It's mapping simultaneously uh, as it is localizing. Then below you can see Monte Carlo localization, where you maintain multiple hypotheses of of the robot's position and orientation within a mapped world. So if you have observed previously, then you would be able to see that these red dots would have started completely distributed within the world, and as soon as the robot senses it moves through the world, the number of hypotheses possible hypotheses based on the previously observed data gets reduced, and basically we localize the robot. That's called Monte Carlo localization. Okay, so what skills do you need for this area? Same ROS experience, C++, Python, and simulators like Gazebo. You need CUDA as well. And here you need familiarity with concepts like probability theory, data structures and algorithms, and nonlinear optimization as well. And here hardware components play a huge role as well. So if you have familiarity with ASICs, which are application specific integrated circuits, and FPGAs, which are field programmable gated arrays, that would be a massive plus. And avenues for jobs, you could work at these companies. MSN is quite a great company. It works for mapping subterranean regions. And there's General Dynamics as well, which develops unmanned underwater vehicles. And for higher studies and research, you could go to the NAV Lab Stanford, you could go to TU Munich, University of Texas. There's a SLAM lab there. And you could go to Purdue as well, Scalar Lab at UPenn. So this is about planning, mapping, estimation, and localization. And now we come to dynamical systems and control. So what's the purpose of control? Why do we need a control system for our robot? So for any robot to execute our commands, the user commands, and execute a desired motion or something, it should be able to do it perfectly, right? So we need a control system that regulates the system behavior and minimizes error with respect to the user commands. And there are a lot of applications for control systems. It's present in almost all of the industries. We have process control, which is useful in chemical manufacturing plants. There's locomotion in bipeds and quadrupeds, attitude control in space, how the reaction wheels should operate in order to maintain the orientation of the satellite or the spacecraft. Then challenges within this field include we have a lot of traditional controllers that like PID that can be used for a lot of systems, but there are certain systems with non-linearities with which PID cannot be used. It simply cannot model the behavior of a nonlinear system with a theory that was built for linear time invariant systems, basically. So that's a challenge. Now, efficient real-time implementation of advanced control techniques is also a challenge. These techniques can include uh, receding horizon control, uh, which means I'll explain what that means. An example for receding horizon controller is a nonlinear model predictive control. So there are three words here: model, predictive, control. So we have a model of the robot or any system, and using that model, we can make certain predictions based on the control input that we can give to the model, right? So in MPC, what we do is based on the model, we have the ability to predict what the system would do, and we optimize over the space of all the possible control inputs to the system in order to find the optimal control input, which minimizes the deviation between the desired path that the model should take and the predicted path. So you have to do this optimization at every time step, basically. And for stacks which are working at 30 hertz or something, it would this optimization, this nonlinear optimization, has to happen 30 times a second. That's quite a challenge for real-time implementation. So if you wish to take a deeper look into model predictive control, I recommend you to watch this video by Steve Brunton. He explains it quite well. Okay, so skills you need for getting into this area. Similar ROS experience, C++, Python, and simulators like Carla and Gazebo. You also need to have a background in control systems, obviously, and also familiarity with nonlinear optimization, model discovery, and some concepts in chaos theory help as well. Right. So for jobs, you may go to these companies. There's Fanuc, Honeywell, General Dynamics, Emerson, Rockwell Automation, which is for industrial automation, obviously. Then for higher studies, you could go to Boston University, WPI, Binghamton University. You could go to Santa Clara as well, and there's an Applied Dynamics and Optimization lab at New York University, NYU. So finally, we have mechanism design. So why should we care about developing and studying mechanisms? This is because mechanisms are very powerful tools in robotics and even automation engineering, and they can generate arbitrarily complex motions with very simple actuation. As you can see on the left, there's a simple rotational actuation here, and with that actuation, the compliant mechanism is generating a complex motion like this walk cycle, right? And here also there's a vent mechanism. There's a simple rotational actuation here, and that operates all of the fins here. So that's why mechanisms are very useful. Applications include, the James Webb Space Telescope that was deployed. That will be deployed, I guess. So it's sun shield that yeah, uh, I think James Webb Telescope has already been deployed, and it's towards going to the Lagrange point. It has been designated to, and so the sun shield that was developed for the James Webb Space Telescope to deploy that sun shield, we have a mechanism. Then there's oxidic materials as well, which are materials which are mechanical metamaterials that have negative Poisson's ratio. So these are fascinating materials. And then you have underactuated grippers, animatronics, which is used in the special effects industry, then industrial automation as well. So here are a few problems that you can work on if you wish to get into mechanism design. So you can develop micro mechanisms for mechanical metamaterials, like I mentioned, oxidic materials. Then uh, the field of parallel robots and parallel mechanisms is not that much explored as serial robots are. So the analysis of singularities and their topological effects and on the workspace of the parallel mechanism or robot has not been studied very extensively. So you can work on that area. And I would recommend you to watch this video on branched scissor mechanisms by Henry Segerman. It's quite an interesting mechanism. So the skills you need for mechanism design. So this field involves multi-body dynamic simulations, so you need familiarity with that. So softwares like MSC Adams or COMSOL Multiphysics would play a role here. Similarly, you need a familiarity with finite element methods as well, and formats like URDF and Collara, which can be used to model any kind of serial robot or linkage and so on, any mechanism. And intuition in origami would be a plus. Then for jobs, you could work at Boston Dynamics, Wolfram Research, Raytheon Technologies, Penta Robotics. And for higher studies, you could go to the Geometry Computing Lab at EPFL. This is, I think, one of the most fascinating and fun labs in this area. And it has a YouTube channel as well. I would recommend you to check it. It's quite interesting. Then you could go to CMU, ASU, which is Arizona State University, Brown University, then McGill, and you could go to USC as well, University of Southern California. And we have now looked at robotics. So let's take a look into artificial intelligence. Right. So what fields exist within artificial intelligence? What areas are there? So we have machine learning first, which is quite a vast field, and we'll discuss in detail about it. Then we have natural language processing, which involves dealing with uh, natural language, of course, human interpretable language. So then we have evolutionary computation, where algorithms and optimization techniques based on biology are used. Like say we have genetic algorithms, and then we have computer vision, which we have already discussed, and finally we have knowledge discovery and data mining. We'll look at all of these areas in detail. So let's start with machine learning. So why should we care about machine learning? Right. So there are certain problems around us for which it is infeasible to explicitly program a computer to solve those problems. For example, we have a vision task. The computer has to understand an image it is seeing, and based on that interpretation or an internal representation that it has to perform perform some operation or have some decision. So with ML and associated methods models, we develop techniques such that a computer can gradually learn to solve a problem and even outperform the humans, at the human level of uh, you know the ability of humans. It can outperform. Then there are a few broad areas within machine learning. There's supervised learning, unsupervised learning, and reinforcement learning. So within supervised learning, there are two classes of problems. We have classification problems and regression problems. This is based on the format of output that we need from the machine learning model. So here, you would be using, support vector machines, random forest classification, classifiers and regressors. And then we have decision trees, techniques like AdaBoost and k nearest neighbors as well. Then we have unsupervised learning, where we don't provide any labels explicitly. So here we study the clustering among the data, and we try to reduce the number of dimensions of the data in order to process it faster. So there are a few dimensionality reduction techniques like PCA, which is principal component analysis. There's LDA, which is linear discriminant analysis. There's autoencoders as well, which is a which is a network architecture which can map a high dimensional data into a low dimensional latent space. So this is naturally used for data compression as well. Then we have reinforcement learning, where we train an agent to behave ideally in an environment, and we reinforce its desirable behavior and punish it when it does something wrong. So it learns using that mechanism. So here we would use techniques like Monte Carlo, Q-learning, and Markov processes. Then applications for machine learning are widespread. We have time series forecasting, which is relevant for weather patterns, financial modeling, and so on. There's exoplanet atmosphere characterization, insurance calculations, recommendation engines. We have Spotify and YouTube for that. Then there's drug synthesis as well. Then we have sentiment analysis, uh, based on which you can trade in the financial market. And so on. There are too many applications to list. So if you're just starting with machine learning, I would recommend you to watch this. Was Like, check out the channel by Josh Tamer. It's called StatQuest, and he covers ML fundamentals very intuitively. And on the left side here, you can see the output from an ML model called a GAN, which uh, uh, which stands for Generative Adversarial Network. This architecture is able to generate new data from its training data, and here in this case it's face generation. So uh, its task is to approximate a low dimensional data, a probability distribution in high dimensional space. So interpolation between any 2 points within the latent space corresponds to the interpolation between faces, and that's what you are seeing here, how the faces are morphing into each other, right? So what uh, what are the challenges within machine learning? So if you take a look at reinforcement learning specifically, there's a problem called the reward hacking problem. So let's just say we have an agent that is trained that is to be trained to play a particular game. So quite often than not, what happens is that agent tries to maximize its reward by exploiting the bugs in the physics engine of the game, right? And it does not perform uh, according to an optimal human player, what the human player would do. That's a reward hacking problem. So that means that we cannot exactly specify uh, what the agent should do, and that's the reward modeling problem as well. So then we have learning from limited samples, effective training with sparse rewards. So and then we have instrumental goals and safety issues with real world agents. So what are instrumental goals? Basically, let me give an example. We have an agent that has a task of collecting stamps. It's a physical agent, and its task is to collect stamps and collect as many as it can. And what happens is, over time it collects a lot of stamps, and we think our requirement is fulfilled, and we try to switch it off. Then what happens is, the agent prevents us from switching it off, because that would ultimately lead to it getting no rewards. It's always trying to maximize its own reward, and switching it off would cut its reward. Similarly, modifying its reward function would also cut its reward. So that uh, so preventing us from switching it off and modifying its reward function are the instrumental goals of the agent that help it gain its that help it reach its terminal goal, which is collecting stamps. So when these instrumental goals do not align with our goals, then that creates safety issues. Then we have to develop better techniques for hyperparameter optimization. Then we also have to figure out how to handle multimodality within data. So combining heterogeneous data like audio, visuals, text, and so on within the same model. Then we have to develop interpretable models. Basically, we have to make sense of billions of parameters. Just like, for an example, there's GPT-3 that was recently launched, and it has billions of parameters. But that model is essentially a black box. It gives us no intuitions so as to how it works behind the scenes. That's the interpretability problem. Then avenues for jobs include, you could go to companies like OpenAI, DeepMind, Amazon, AlphaSense, which is a financial trading firm that uses AI, and Genesis Therapeutics does novel drug synthesis. Then for higher studies and research, you could go to these places: University of Michigan, the famous CSAIL at MIT, UCLA at U Berlin, CMU, University of Stuttgart, there's Cornell NLP Group, and there's a Turing Center at University of Washington as well. So now we have natural language processing. So what are the goals of NLP? We have to achieve human-like comprehension of text and languages for computers to be able to understand, understand, summarize, translate, and draw accurate inferences from the text or speech they are presented with. Right. So there are a few broad areas within NLP. Firstly, there's text and speech processing, which includes techniques like OCR, optical character recognition, speech recognition. Then there's speech segmentation, like segmenting speech into individual syllables and then labeling them. There's text to speech as well. Then there's another area called morphological analysis, which deals with the structure within sentences and how each each component within the sentence functions in the sentence. So that includes morphological segmentation, part of speech tagging. There's sentiment analysis as well within lexical semantics, which is often used in the industry, and additional problems like word sense disambiguation. That means uh, resolving ambiguities between words in a sentence. Then there's terminology extraction as well for text with domain-specific language. Then applications include autocorrect, autocomplete, algorithmic trading based on market sentiment. That's also an application. Then spam prediction, which Gmail obviously uses. Then we have targeted advertising as well, which Facebook and Google both are using. And recently, I think a novel architecture called WaveNet was developed, which can do speech generation and speech cloning with just 5 seconds of training data. Isn't that fascinating? So this is the video based on that. Mm. You should watch it later on. So there are a few challenges within NLP. We have to handle colloquialisms and slang within languages. These are basically outliers within the training data set, and their little meaning could be misleading. Then handling domain-specific language and jargon is also a challenge. Handling ambiguity in speech. Let's just say we have the sentence, "The man saw the girl with the telescope." This sentence could mean two things, and the actual meaning would depend on the context, the underlying context that the sentence has. Then there's a talk by Microsoft Research on the learning challenges within NLP. You should watch it later on. Then for jobs, you could go to OpenAI, Amazon, Apple, and here you have Duolingo and Babbel as well, which are language learning apps. And obviously, they are using speech processing within their apps. So for higher studies, you could go to Cornell, University of Stuttgart, at UIUC, University of Massachusetts, UCL in the UK, University of Oxford, and there's UT Austin as well. And it's in Texas, by the way. So moving on, now we come to evolutionary computation. The goals of evolutionary computation are is to develop nature-inspired techniques and heuristics for solving very high dimensional nonlinear global optimization problems. So let's take a look at each of these words here. There's high dimensional. It means that there are a lot of control variables involved, a lot of parameters involved that could vary, and we have to find an optimal solution within that high dimensional space that maximizes or minimizes a particular objective. Then we have nonlinear. The objective function may be non-linear. It might not be differentiable as well. So in that case, you need derivative free methods. And for global optimization indicates that the methods that you use should not converge to local optima, right? And you should try to find the global optimum instead. Then there are some evolutionary techniques. There's ant colony optimization, which is based on the hierarchy of ants, their foraging behavior, and their communication process using pheromones. So we have particle sum optimization, which is based on flocking behavior of birds, along with there's individual bird cognition as well. Then there's neuroevolution, which for a given task generates the optimal artificial neural network architectures and topology in order to tackle that problem. Then we have the famous genetic algorithm, which is based on the principles of crossover, mutation, and the selection mechanism. So on the left side here, you can see we have a very bumpy function called the Ackley function, and differential evolution is also an evolutionary optimization technique, which uh, which is a global optimization technique. In this case, there are a lot of local minima here, but the algorithm efficiently finds out the global optimum here, shown here. Then we have very difficult problems, NP hard problems, like the traveling salesman problem, which cannot be easily solved with conventional algorithms. So we need uh, heuristics based algorithms like the genetic algorithm here, which is able to solve it within reasonable times, right? Then applications include program synthesis, which means generate a program that accomplishes a particular task with the minimum computational requirement, minimum storage requirement, minimum complexity, and so on. That's called program synthesis. Then we have gate generation for quadrupeds and bipeds. We can optimize their gate using evolutionary computation as well. Then we have evolved antenna design, which is an antenna design process which uses evolutionary computation basically. Then we have topology optimization for mechanical structures, evolutionary robotics, and for an eye candy here, you can watch this mesmerizing video by Sebastian Lag on ant and slime simulations. It's quite beautiful. So there are a few challenges within evolutionary computation. Firstly, there's a lack of reproducibility. That means there's non-determinism as we are using, randomness to find the optimal values for an objective function. So every time you run the program, you might get different results. So then there's a need of extreme tuning when it comes to multiple objectives, which may potentially conflict with each other. And there's also a theorem called the no free lunch theorem in this area, which states that for all black box search heuristics or black box optimization algorithms, they have equal performance when that performance is averaged across all the possible discrete optimization problems. So this means that if you find an algorithm working better for a particular problem, then it's very likely that that same algorithm would function very poorly on some other problem. So all such search heuristics have on an average an equal performance. So for additional details, you could check nofreelance.org. And for jobs, you could go to Cognizant, Reverie Labs, Verikai, which is an insurance firm that uses AI. High Hedge is a financial firm that uses evolutionary computation as well. Then, for higher studies, you could go to the University of Exeter, KIT in Germany, Colorado State University. There's Michigan State University as well, and you could go to Kanpur Genetic Algorithms Laboratory, which is at IIT Kanpur. You could go to UCSD, and there's Kanpur Genetic Algorithms Lab as well. So now finally we come to knowledge discovery and data mining. So what's the goals of knowledge discovery? We have to develop techniques and processes that extract potentially valuable information from unstructured data sets. And we also have to find structure and patterns that make sense to us and that enable us to make valuable decisions in the future. So there are some problems within data mining that are generally common, and the first one is outlier analysis. So this is generally used in burglar detection, tax fraud detection, and then we have association rules, where we model the co-occurrence of two events and their likelihood. Basically, this is used when a particular product is bought, then what all products are likely to be bought with that product. So these are association rules, and uh, these are used quite a lot in e-commerce websites. So then we have sequential pattern identification, which requires which helps in modeling recommendation engines. So we have Spotify playlists, which arranges a set of songs in a particular sequence to optimize the the enjoyment that we get from listening to those songs, right? And then we have predictive analytics, which is useful for obviously economics and supply chain management. Applications include sales optimization, like I said, prospective customer identification, adaptive education. There's financial risk assessment as well. Then I would recommend you to watch this video on data mining in healthcare, which is a talk by Dr. Herbert Chase. And coming to the challenges within data mining. Firstly, this is quite a controversial topic and leads to a lot of privacy issues. Data mining, these big corporations regularly collect our data and uh, violate our right to privacy. So, what if there could be a mechanism through which none of our private data would get communicated, would be tracked, and still the corporations could get the information they need. So that's the good use case for zero knowledge data mining, where certain cryptographic techniques can be used. Then robustness under noisy and incomplete data. This is a challenge as well. Tackling the curse of dimensionality. So the curse of dimensionality is prevalent in basically all the subfields of AI, and it calls for efficient scaling in distributed data mining. So then we have mining interesting knowledge in end user perspective. So what do I mean by interesting here? So if there's an end user that does not have any domain knowledge related to data mining, but still he or she wants to extract important or interesting knowledge from the data he or she has, then what interesting means in his or her perspective varies, and encapsulating that is quite challenging. Then for jobs, you could go to Oracle, IBM. There's Orange Data Mining, Nime Analytics, right? And for higher studies, you could go to Oxford. There's a data mining research group at IBM. Then genetic algorithms group, Colorado State University. And Microsoft Research has a data mining department as well. JPL, which is the Jet Propulsion Laboratory, and IIT Roorkee also has a data mining lab. So, finally, let's look into the field of space technology and what all fields exist within space technology. We have propulsion systems, then there's flight computing, avionics, navigation, and control. So this is basically all of the electronics that is responsible for the entirety of the spacecraft operation. Then we have human health, life support, and habitation systems. These systems are quite important if astronauts are involved within the mission. Then we have sensors and instruments which enable us to carry out scientific experiments out there in space, right? So coming to propulsion systems, what is this area about? As the name suggests, this area covers the technologies for both chemical and non-chemical propulsion systems and the related ancillary systems to these propulsion systems for space launch and even in-space propulsion applications. So what are in-space propulsion applications? Like attitude control, we have reaction thrusters, which try to maintain the orientation of the satellite or spacecraft in space. So you need a propulsion system for that. Then we have launch, of course, propulsion systems are needed. Mechanism deployment, like I said, for I think James Webb Space Telescope, we have. Then for performing orbital maneuvers as well, we need thrusters. Then there are a lot of challenges within this field. Firstly, a lot of propulsion systems that exist right now operate on the deflagration based mechanism. Deflagration is basically a rapid combustion process, but developing detonation based propulsion, which involves shock waves, harnessing the energy from shock waves, that has been quite challenging. So there's an engine called the RDE, rotating detonation engine, which has an annular combustion chamber in which shock waves are perpetually sustained using periodic fuel injection and so on. That engine has not been deployed at full scale yet. But that what's the benefit of detonation based propulsion? Its efficiency is considerably higher. with respect to deflagration based propulsion. So that's the challenge here. Then developing a sufficiently cooled and a simpler to manufacture aerospike engine. Basically, aerospike engine has efficient exhaust expansion at all altitudes. So the GIFs that have linked here, they use a standard converging diverging nozzle, and that's how they expand and accelerate the gas uh, coming out of the nozzle. So the nozzle geometry is fixed, right? So the expansion that happens, the gas expansion that happens, there has to be an optimal expansion ratio for the gas at a corresponding temperature. So as we know that with altitude, the pressure changes, of course. So this nozzle, this fixed nozzle, is quite inefficient at almost all of the altitudes, and it's very efficient at a particular altitude. Whereas these aerospike engines do not have this nozzle structure and have efficient exhaust expansion at all altitudes, right? So developing aerospike engines is also a challenge. Then design of efficient non-conventional propulsion systems like ionic propulsion, for relativistic interstellar travel. That is a challenge. Then within the watch section, you could take a deeper look into rotating detonation engines and how the shockwave timescales and everything works. You could get an idea within this video. It's by Steve Brenton, and the second video is on how GPUs were specifically used for a complete full-scale simulation of SpaceX's Mars rocket engine. So that is quite a computationally challenging task, and how they leverage techniques like wavelet compression and sparse grids and so on. That is quite a detailed and insightful talk. So the skills you need for developing propulsion systems is obviously a familiarity with fluid mechanics, gas dynamics, computational fluid dynamics concepts, vibration theory, because there's a lot of vibration and your systems need to work under that. And then there's chemistry of combustion, of course. Then you need familiarity with simulation softwares like ANSYS Fluent, COMSOL Multiphysics, and CATIA. C++, Python, and MATLAB proficiency is expected as well. Then for jobs, you could go to almost all of these companies are Indian companies except SpaceX. There's Agnikul Cosmos. This is the ISRO Propulsion Complex. There's Bellatrix Aerospace, Dhruva Space, and then SpaceX. And for higher studies, you could go to higher studies or research. You could go to ISRO's Propulsion Complex, Computational Aerosciences Lab at the University of Michigan. ISC has a propulsion group as well. There is the Thermal Propulsion Systems group at Oxford, and you can join IIST as well for masters in aerospace engineering. You go to UIUSC, Jet Propulsion Lab at NASA, then the Propulsion Lab at European Space Agency. Now, coming to flight computing, avionics, navigation, and control. What is this area about? This area covers all of the unique electronics, all of the computing hardware that is involved in flight systems, and these can be used in space or within atmosphere as well. And these systems are responsible for tasks like navigation, thermal management, telemetry of data, flight data logging, and so on. Correct. So the applications include course correction, staying on the right trajectory so that uh, you know proper orbital altitude and so on. Then flight data logging is there, command handling either by the astronauts or the ground station, ascent and descent monitoring, which is a crucial operation. Then what challenges you might face within this field? Firstly, space debris is a huge problem, and it has to be detected in an active fashion, and the collisions have to be prevented because collisions can be catastrophic, and it can puncture the spacecraft and cause all kinds of damage. Right. So then, maintaining cryogenic temperatures for electronics in extreme environments. Again, let us take a look at James Webb Space Telescope. It is an infrared it is sensitive to the infrared region. That's why it is very sensitive to heat. That's why it has the particular sun shield that it has. And to minimize the thermal noise, its sensors and electronics have to be kept at cryogenic temperatures within space. So that is quite challenging. Then developing electronics that is resilient to space radiation, cosmic rays, and doing that while improving the performance of those electronics is quite challenging, because cosmic rays are often notorious to cause bit flips and system crashes within the within space, and you cannot afford to have system failures when you are doing crucial operations within space, maneuvering, and so on. So watch this insane video on the engineering of James Webb Space Telescope. And okay, right. So this, for the skills that you need to get into this field, it would include topics like control theory, estimation theory. There's a very large scale integration, that is VLSI design, power electronics, computer networking is essential as well. Then there's wave propagation and antenna design, digital signal processing. Uh, this is quite a lot of requirements, right? Then for jobs, you could go to Bharat Electronics, GE Aviation. There's HAL as well, Antrix Corporation, and you could join Boeing as well. Then for higher studies or research, you could go to ISRO Satellite Center, Bangalore, Satish Dhawan Space Center, VSSC, which is the Vikram Sarabhai Space Center at Trivandrum. You could do an MTech in avionics at IIST, and flight mechanics and control groups. There's this group in Georgia Tech as well, and avionics lab at both NASA and European Space Agency. So this is about flight computing, avionics, navigation, and control. Then we have human life support, human health, life support, and habitation systems. So the key goals of this area is to develop technologies that are specific to the human element, of course. So these technologies directly affect the crew needs, their survival, their well-being, and it also includes the environment and all of the interfaces that the crew encounter. So all of these systems have to be optimized for space use, and a certain number of crucial tasks it has to satisfy, like CO2 scrubbing. Of course, if you don't remove the CO2 from the atmosphere, its concentration would gradually rise and lead to CO2 poisoning eventually. Then there are HVAC systems, which is heating, ventilation, air conditioning systems, which is necessary in space as well. Then there's wastewater recycling. You cannot afford to lose a single drop of water within space. Then there's poisonous gas trace detection and healthcare within space. And coming to the challenges, the current state of the art spacesuits have quite limited mobility, and the challenge is to develop such spacesuits uh, that provide the ideal dexterity to the astronauts while spacewalks, doing extravehicular maintenance and so on, and that should minimize the amount of fatigue that the astronauts feel. Then developing quick and viable methods for large scale terraforming of planets. So if we plan to colonize a planet like Mars, then we need to potentially convert its atmosphere for it to be suitable for human living. So how do we terraform planets is a challenge to figure out. Then countering bone density loss and other adverse health effects which occur due to extended zero G exposure. There have been a few methods for this, like exercising, as you can see here. Uh, it prevents bone density loss to some extent, but effective methods have not been looked into. Then we have to shield humans against radiation, solar winds, and cosmic rays as well, because certainly they can cause cancer over a long period of time. Then enabling human hibernation for long-term space travel. This technology is quite far-fetched and uh, even a part of science fiction as of now, and no uh, like good progress has been made in this field. Then you could check out NASA's environmental control and life support system in this video, how it works and so on. And the skills you need for this, for developing such systems, basically familiarity with HVAC systems, concepts related to respiration or metabolism, uh, even novel methods for agriculture, fluid mechanics, human physiology. This is quite an interdisciplinary area as it requires a lot of knowledge from different fields. Right? Then you also need to know tools like Simulink and Nastran, which are used by NASA and ISRO, obviously. Then for jobs, you could go to Paragon Space Development Corporation (ILC), which develops space suits for astronauts. There's Honeywell, SpaceX, Lockheed Martin, and for higher studies, you could go to the ISRO Space Applications Center. You could do a PhD in life support systems uh, at the Melissa Foundation, which is a foundation set up by the European Space Agency. Then you could go into bioastronautics at the University of Colorado, Texas A&M, Cornell as well, and also do some courses like the Project Possum courses, which are specifically made for uh, designers of life support systems, habitation systems, and so on. Then, finally, let us come to sensors and instruments. This area covers technologies for instruments and sensors, which enable the mission to carry out remote observation, scientific measurements in space, imaging, and remote testing as well. So here are some applications for what these sensors and instruments could be used for. We have drilling operations like you can see here in the lower left corner. Uh, it depicts the drill that Curiosity had, which it used on the surface of Mars. So you have drilling operations. There's multispectral imaging, which a lot of our Indian satellites do. Then there's space dust sampling as well, measuring radiation, magnetic fields. There's barometry in foreign atmospheres, high gain antennae development. There's subsurface radar mapping as well in order to determine if there are any potential water sources beneath the surface, right? And there are a lot of challenges within this field. Basically, we have to improve the spatial and temporal resolution of all of the remotely sensed data. Take an example of the Google Map update frequency. It's certainly not the case that we get the updated data on a daily basis on Google Maps, right? So that's quite a bottleneck, and hmm. so it's difficult to protect sensitive instruments against shocks and radiation as well. So why shocks? Because during launch, there's a uh, very violent vibration. The instruments are subjected to very violent vibrations, and then when they reach space, they are no longer protected by the Earth's magnetic field, so they are affected by radiation as well. So, in this case, take a look at the Kepler Space Telescope and why its bearings failed, because it had a set of reaction wheels basically, and each of these reaction wheels naturally had bearings, and it was found that all of these bearings for all of the reaction wheels failed one by one, and the maneuverability of Kepler Space Telescope was lost. And later on, it was found that uh, these bearing failures were happening due to cosmic rays and space radiation. Basically, it was leading to building up of charge within the bearing races, and that led to electrical discharge eventually, which led to uh, material removal from inside the bearing, which eventually clogged the bearing and prevented it from rotating. So that's how Kepler Space Telescope bearings failed. And then we have difficulties in predicting operational environments as well. For example, we have the Rosetta mission failure. The goal was to land on a comet, and what happened actually was, as naturally a comet is a very small body, gravitationally speaking, so it's very difficult to land on a body that has very negligible gravity. So what actually happened was the probe that was sent actually collided on the surface, comet surface, and got stuck under some rocks, and it was lost for many years until later it was the contact was established. So these are the challenges that we have to tackle. Now, skills you need for developing sensors and instruments. If it's uh, if it's in the electronics and electrical sector, you would need skills in VLSI design, antenna design, wave propagation, communication, testing, power electronics, and even MEMS systems nowadays, because a lot of the sensors are being miniaturized and integrated into MEMS systems. Then we have if we have the mechanical side. If you look at the mechanical side of things, then one needs to have knowledge in metallurgy, manufacturing processes, vibration theory, control systems, and obviously robotics. Right. Then these are the companies where you could work at for developing sensors and instruments. There's Pixel, which is an Indian startup that develops microsatellites for hyperspectral imaging. You could go there. That's a quite a great company. And there's SpaceX, Lockheed Martin, Agnikul, Cosmos, Dhruva Space. And for higher studies or research, you could go to ISRO Inertial Systems Unit, where that's the place where I worked. And we have Vikram Sarabhai Space Center, ISRO Space Application Center. There's also an ISRO lab for electro-optics. You could go there as well. And there's Indian Institute for Remote Sensing. You could go to Johns Hopkins for at the Applied Physics Lab. This lab actually supplied a few key components for the Perseverance rover. Then we have Space Sciences Lab at UC Berkeley. So this is about the field of space technology. We looked into artificial intelligence. We looked into robotics. We and hopefully I was able to give you a bird's eye view on these all of these fields, and hopefully motivate you to pick up interesting projects in these fields, and potentially tackle some challenges that I've discussed. Thank you. So if you have any doubts, feel free to reach out to me. I'm on LinkedIn as well. So that's where you could contact me, and so that's my talk. Thank you.
Thank you so much, Devashish, for a
Yeah.
wonderful session. I hope this session is very useful for all the participants. Uh, so I would like everyone to, like, if you have any questions, you can ask Devashish. And yeah, so uh, it was a very insightful session. And regarding the projects and the topics, yes, Gaurav will be sharing the recording on our YouTube channel as well as the PPT, so you can access the PPT from there as well. And also, like, so as Devashish, the topics Devashish talked upon, we are also working on those projects only. So currently, we are working on three different types of projects where we are using like building a computer vision system for the lunar exploration. Another project is on developing a system for determining the size of an asteroid. And along with that, we are also working on the space image processing workshop. So guys, if you're interested in all of these projects and joining with this Spartificial community, you can directly go to our website, which is www.spartificial.com, and enroll in these projects. There are a lot of opportunities further at Spartificial, so you can check our website for the same. So there is another question. Just a second. Okay. So this question is from Dhirendra. It is, sir, SpaceX is only employing American nationals currently, right?
Yeah, that is happening, right? So a way around that would be if you could go for a master's in the US, that is preferably near to a Tesla site or Tesla location. Then, oh, sorry, Tesla Spaces. Okay, so you could easily intern there there is a thing called OPT, which is optional practical training, and CPT, curricular practical training, and un- under that you could actually intern at those companies and uh, get I think get an H1B sponsor from SpaceX.
Also, I would like to shed some more light on this topic because, yeah. So you can't get a job in SpaceX without becoming a US citizen, because it comes under their ITAR policy, and there is a restriction because of the defense. SpaceX falls into rocket technology and it is under the defense. So if you want to get into SpaceX, you need to be the citizen of US. So but there are a lot of more companies in the US as well as in India where you can work on the same topics as well. So there is another question from Anugia. Is it possible to do masters in aerospace engineering after doing BTech in EC?
Mm, I think if you have done relevant projects, and if the masters is in the US or something, where there's a holistic application process, there you could tell your own characteristic story, and you could, you know, convey your motivation for doing an aerospace masters in aerospace engineering, and that heavy lifting would be done by your SOP, your letter of recommendations, and so on. So it's certainly possible. I think I know some people uh, that have changed paths in a similar fashion.
Yes, I also agree to Devashish. Like you can switch to different masters. Like if you want to go in aerospace, you need to show some relevant projects or internships, and you can also mention the key motivations to do a masters in aerospace in your SOP as well. So as the foreign countries have a holistic approach to the application process, it is possible to switch your masters. So yeah. Anyone else? Okay, then we'll be wrapping up this session. But before that, I would like Yash to speak, have some words for the session, and I'll be dropping the Discord link to our Spartificial community. So if you have any doubts or if you want to know about the future programs, you can get to know from that. We have a great community of individuals who are interested in AI and space science. So I'll be dropping the link to our Discord channel in the chat box only. Just a second. And till then, yes, you can have a talk with Devashish or the participants.
Yeah, hi Devashish. Thank you
Hi,
so much for the
thank
amazing
you.
talk. And yeah, I think it's very beneficial for all the students and all the participants also. So,
Thank you.
guys, if you have any more doubts, you can ask. And we have Devashish with us for now. And okay, so the recording will be published on our YouTube channel along with the presentation also. You guys can check it out from there. And again, thank you so much, Devashish.
Thank you.
And it was very, very insightful. And yeah, thank you so much, everyone.
Okay, I'm dropping the link for our Discord server. So you can join our Discord server or you can visit our website. Yash has already mentioned the URL for our website, and you can check our upcoming projects as well as be a part of our community. We have a lot of internship opportunities also coming upon, and we'll have some more sessions, expert sessions as well. So thank you once again, guys, for joining in. Thank you, Devashish, for your wonderful time.
Thank
I
you.
guess, yeah, it was a wonderful session. So thank you, guys. Now, okay.